Hello, welcome to this math extra credit video. Today we will be discussing total distance versus displacement. These are both concepts within the integration unit and are both used to find the area under a curve. Displacement is a vector, which means it takes into account signage, while total distance is a scalar and it disregards signage. This means that when calculating the total distance, you must consider the intervals where the function is less than 0 and the intervals where the function is greater than 0. To calculate the total distance traveled, you must integrate the absolute value of the function, while when finding displacement, you must just find the normal integral. Here we have an example. For the displacement from a to b, that interval, the integral of that function is a1 minus a2, since a2 is under the curve, plus a3, because a1 and a3 are above the curve. However, with the total distance, you're taking the absolute value of the function, which means it disregards whether the function is under the x-axis or not, which means that the integral of this function is a1 plus a2 plus a3. Okay, so this is our first example. So the problem reads, find the displacement and total distance of the function negative x squared minus x plus 2 on the interval 0 to 2. So first, when finding displacement, we're just going to take the definite integral. So what I've done here is written out the definite integral and then found the antiderivative, which is negative 1/3 x cubed minus 1/2 x squared plus 2x from 2 to 0. This then solves to be negative 8 over 3 minus 2 plus 4 minus 0, which is equal to negative 2/3. This is our displacement. Now moving on to distance. To find distance, we need to find the point at which the graph goes under the x-axis, which means we need to find the x-intercept. Since the interval begins at 0, the only x-intercept that could work is 1. So you can see here that I've solved it to find negative x minus 1 times x plus 2, which means that the only viable x-intercept would be x minus 1. This means that we are going to integrate the first half of the function from 1 to 0 minus the second half of the function from 2 to 1, because this part is under the x-axis. So as you can see, I've done the work here. This is the antiderivative. It's the same antiderivative as it was in displacement, minus the same antiderivative from 2 to 1. The first one was 1 to 0. This eventually solves to be 7 over 6 minus 0 minus 2 over 3 minus 7 over 6. This eventually solves to be 7 over 6 minus, in parentheses, negative 11 over 6, which is equal to 3. 3 is our total distance. Here is the sign chart for this function. As can be seen, between 0 and 1, the graph is positive, and between 1 and 5, the graph is negative, meaning that there are two separate parts for this graph. Example 2. A particle moves in a straight line with velocity v of t is equal to 5 minus t meters per second. Find displacement and total distance from t equals 0 to t equals 10. So for displacement, once again, we're going to be taking the normal integral from 0 to 10, since those are our x values. Once I took the antiderivative, which happens to be 5t minus t squared over 2, I then plugged in both 0 and 10. The answer ended up being 0 meters, because this graph is a linear equation where exactly halfway, the graph transitions to under the x-axis. So counting signage, the entire displacement is 0 meters. However, for total distance, we would be taking the absolute value. So I set this function equal to 0 right here, and I found that the middle value is at 5. That means that we will be solving the integral from 0 to 5, which is halfway, and then the minus the integral of the other half, which is 5 to 10, right here. Once I found the antiderivative, which was the same thing as displacement, 5t minus t squared over 2, I then plugged in the numerous values and solved it so that the total displacement or total distance is 25 meters. Here is the sign chart for this function. As can be seen, before 5 the graph is positive, exactly half, and after 5 the graph rises or drops below the x-axis and is negative. So, for example 3, the problem asks us to find the total distance and displacement of the function v of x is equal to x squared minus 6x from the interval 0 to 6. To find displacement, as usual, we will be using the normal definitive integral. First, I found the antiderivative, which was x cubed over 3 minus 3x squared from 0 to 6. I then plugged in the values and found that the displacement is negative 36. Now for total distance, once again I solved for the x-intercepts, but the x-intercepts happen to be the endpoints for this interval, 0 and 6. Now, this graph does not rise above the x-axis, as can be pointed out by the sign chart. I took two random values from within the interval, and both resulted in a negative output, meaning that the graph does not rise above the x-axis and is negative the entire time. So, total distance is then same as displacement, but is positive because you're taking the absolute value of the function. So, you may ask, why is this a relevant concept in real life? There's a clear physics application as seen by one of the examples, I believe it was example 2, where we find the displacement versus distance of a particle. This allows us to find information about the particle's movement, which may help in further problems about that particle. Another example is that the total area under a curve for a force versus time graph is the impulse of that graph. So those of us in physics will know that we were required to count the boxes under the force versus time graph to find impulse. However, we can use the total distance equation and find the total area under the curve in order to find the complete impulse as well, using integration.